Okay, picking up where we left off, we spent all of yesterday basically doing commutators with angular momentum. And now we get to stuff that is frankly kind of annoyingly difficult, and yet it comes to easy outcomes. And that is finding our angular momentum operator in spherical coordinates. So we have our definition of angular momentum in 3 dimensions right there. It's R cross P, and so putting in our momentum operator minus I h bar del, or gradient, and then we have in spherical coordinates, here's what that gradient operator is. And so we first need to say, what is this going to be? So how do we find a cross product? What was our mechanism?
Find the perpendicular parts, so you had to do the matrix.
Yeah. So I'll have E r hat, E theta. This E is just unit vector in the direction of. So these are my unit vectors. And then my R vector. My R vector is actually really simple. I was thinking about this yesterday when I was preparing for class, because obviously I had to have this ready for class yesterday. I intended to do it yesterday. And the R vector, what's the magnitude of the R vector? R. And what's its direction? It sounds very dumb when you say it. So don't feel bad if you're thinking that it couldn't be that simple. What's the direction of the R vector? In the R direction. Right, that's what I said. It sounds really dumb when you say it. And so that's just going to be R0, 0, which makes our cross product a little easier, right? And then we have the components there of the gradient operator, which is this. And so if we do this this determinant now, one might say, well, there is an easier way to do this. If I take this row, I only have to do it once. But the problem is it's going to mix my component directions. And I want how much in each component direction. So I still start with this one. So that's going to be equal to, in the R direction, that's going to be 0, right? And then we have to flip signs. So in the theta direction, we have this. And then finally in the phi direction, and okay. Apparently that's right. Doesn't feel right. It really doesn't feel right. Anyhow, let's just run with it. What could go wrong, right? I like that positivity there. So this is equal to 0 in the e to the r direction. 1 over r, well, the r's cancel. And I have in the theta direction 1 over sine theta d phi. I'm pretty sure I have my phi and my theta backward here. I'm so sure I'm going to check the textbook rather than continuing here because it just does not seem appropriate. I'm like 50 pages away from where I needed to be, it turns out. Okay, theta is, no, that was right. Oh, what did I, okay, my answer does look different than theirs because I have, well, that's what I got. I'm looking at the textbook and it has r cross theta, r cross phi, and then it comes to, whew, on the next page it has what I have. Except for one thing. What did I forget? I forgot the minus IH bar. And so that means everything here is times minus IH bar, and everything here is times minus IH bar. Okay, so there we have the components of the angular momentum operator for the spherical directions. And so here is rewriting what I just did if I had the IH bar there. And then we want to get L squared. Well, how do you get L squared? You square it. And how do you square vectors? Square vectors like this. And so we have to take L dot L is going to be this thing here acting on itself, but it gets, you notice that it looks a little more confusing than you might expect. Yeah, I don't want to spend, we've spent too much time in math the last 2 lectures and haven't gotten to important outcomes. So if you do this L dot L calculation, and the L dot L calculation is, actually, where is it shown? Oh, it's a problem. It's left to you as a problem to do the calculation. If you look at problem 4.21, it says derive equation 4.132, which is the one I'll put here circled in red. Derive that equation from equations 4 1.29 and 4 1.31. 4 1.29 is the definition of LZ, which we have not actually derived, but it's right there. And 1.31 is the L plus L minus. So you can see that it's not a straightforward thing. So I did things in spherical coordinates, and now suddenly we're changing back to Cartesian coordinates. Does that seem odd? It does to me. It's kind of, you probably haven't seen the movie Periscope Down. He tells him he's going to do something like crazy and is asking if they think they should do it. Well, crazy seems to be working so far. It's something like that. Okay, so this is shifting back into X, Y, and Z coordinates. It was an interesting deviation into the spherical coordinates, but we're going to go back to X, Y, and Z coordinates, but we have the Z, the LZ, in terms of the spherical variables, which in and of itself seems a little odd, right? But we're defining the Z direction is the direction that is the axis we're measuring phi from, or not phi from, theta from. And so with that definition, it turns out that the operator L sub Z is actually really simple in spherical coordinates, which is really nice. It's really nice because we know that psi is equal to blah, blah, e to the I m phi. This stuff here is R of R. Oops, that's phi. Theta of theta. With, of course, normalization constants as necessary, times e to the I m phi. So if I want to find my angular momentum in the Z direction, what do I need to do? Here, I'll put the little operator sign over it. What do I do with the operator to find the eigenvalue for LZ?
Find the expectation value of LZ.
Not the expectation value, just to find the value of LZ. Well, what is the operator eigenvalue, eigenstate relationship?
That the operator acting on the function gives the value times the function.
Right. So if I take this operator, which is minus IH bar dd phi, LZ operator acting on psi NLM is equal to IH bar minus IH bar dd phi well, that derivative is only acting on the term that I've written out. And what's the derivative of e to the I m phi with respect to phi? You bring down the derivative of the exponent.
So I am.
Minus I times I is plus I. And so there we have our eigenvalue is h bar n. And so it turns out it's a very simple relationship to get the angular momentum in the z direction coordinate out of your wave function. Now remember, our wave function, because we were able to find this and we returned the original function, that means that our wave function is a function of this operator. And if our wave function is a function of the operator and our angular momentum square is a function, or it commutes with the LZ, then we should also simultaneously be able to find the total angular momentum. So we can find the angular momentum in the z direction, which is actually, remember, I started with the culmination of yesterday's lecture, and we were looking at the relationship between the angular momentum in the z direction and the total angular momentum. So now we have where that comes from. Now, if we were to go and do a similar thing with L squared operator, well, that's a lot more work, isn't it? It is. And so you know what the textbook does? It does what any crafty mathematician does. It kind of goes around in a loop using the raising and lowering operators, and it's kind of convoluted. We're not going to go through it. But see, it's more convoluted. There's my exact quote from my slide. But it comes up with this relationship. So we just showed how this one comes about. That was easy. I'm sorry, my highlighter won't get the whole thing for some reason. And so we can now see what the eigenvalues are. So if you are in state NLM, L tells you exclusively the angular momentum. M tells you exclusively the component of the angular momentum in the z direction. And so far as you know, what does N tell you?
The shell energy level.
Right, the shell or energy level. Now, the next thing we're going to go to is talking about electron spin, because the energies are not just dependent on N. The energies also depend on the other quantum numbers. And so we have to get to spin before we can make sense of that. So let's review what we have learned. Here I've put what the SPDF stands for so I don't forget it. And I put which one is omitted. I said H or I. It turns out it's J that's omitted. So what we've learned about the hydrogen atom. The principal quantum number tells us the energy and the size of the orbital, right? Because it has to do with the radial function. What did N really stand for?
Indicated the maximum value, which
Yeah.
is series term.
It indicated the maximum value where the series terminated. No one ever thinks about that when they're working with chemistry, right? They think about N in terms of this. So that was a mathematical, that's where it came from. But its ramifications for us are telling us about the energy and the size of the orbital. So N equals 1 is a K, 2 is L, 3 is M, and so on in alphabetical sequence.
Why don't we usually see those KLM? I'm not.
In spectroscopic notation, you do. It's in spectroscopy you see it a lot. Chad being in college physics, we just talked about the X-rays, and the characteristic X-ray spectra are labeled like K alpha, L beta, and so on. And the K tells you that it ends in a K shell, and the alpha says that it changed to 1. So if it is a K alpha, it went from 2 to 1. If it was an L alpha, it would have gone from 3 to 2. So we see it in things like that. In fact, it's called spectroscopic notation using it. Okay, so that's what we have for the N. It came from a radial solution. It told us about the maximum number of terms in our radial polynomial, and it gives us this important information. Then we had L, our orbital or angular momentum quantum number, and it tells us what the orbital is. And so you have your L equals 0 is S for sharp, named for sharp nature of the spectral lines. And then L equals 1 principal, I don't know what principal stands for. 2 diffuse, because you had diffuse or more spread out spectral lines when you had things in D. F for fundamental, once again, I don't know. It seems to me principal and fundamental, shouldn't they be similar? And then after that, they don't stand for anything. After that, it's just alphabetical order, and it's J that's omitted. Fundamental orbital. Okay, then we have the L, or the M sub L, which so far we've just called M. And I put here it's the magnetic quantum number because the only way to see anything from this is if you put it in a magnetic field. You put it in a magnetic field, then knowing the orientation of the angular momentum, the orientation of angular momentum shows up as causing a variation in the energy. And so that's what the magnetic quantum number has, is a practical, measurable thing. It tells us when you put a magnetic field, you can see the orientation or the alignment. So that's what we have so far. And I'm guessing that in your chemistry classes, you haven't really talked so much about what these things are really telling you. You only talk about, okay, so this is what the shape of a p orbital looks like. And that's, you probably learned, p orbital is L equal 1, right? But not the underlying things that go with that. We've seen mathematically now how they come about. Yes?
So when you say, I think you were talking about the orbital precessing yesterday, does that mean the electron is precessing within the orbital, or how do we make sense of that?
Making sense of it, I don't know. I'm going to be kind of like with Heisenberg, I'm not sure what path it's taking or what to make of it. But what we can say is its magnetic moment is precessing. And this is the magnetic moment, not of the electron, but of the orbital.
Okay.
And of course, the electron is orbiting, but the electron has its own magnetic moment.
So we're not talking about the electron's magnetic moment.
No, we call that spin.
Okay. No, I don't. Now I'm more confused.
Okay, so this here, the orbital is the electron orbiting around the nucleus. So it has to do with the electron.
Okay.
But it's not the electron's magnetic moment. It's the magnetic moment of the electron's orbit.
Okay.
Because we have two different things that we're going to have to put together.
So the orbit has a magnetic moment?
Yes. Well, okay. The orbit having a magnetic moment is probably what you have been thinking here is the magnetic moment for the electron. And probably the words you're putting to that is what this is. You know that if you have a wire and you have charge going in a circle, that creates a magnetic field or a magnetic moment. That's what this is.
Okay.
And we're going to get into spin right now. So I'll start off with spin. I hope that there's no slides between here and spin on my presentation. It was noted that there were some more variations in when they put a magnetic field that could be explained by the math we've done so far. And so as people were trying to analyze it, they said, well, it's behaving like there's an additional magnetic moment. And they said, well, we know the electron orbiting like this makes a magnetic moment. The electron spin on its own axis should also make a magnetic moment. And so it was proposed that the electron is spinning on its axis, and that's making a secondary magnetic moment that we have to treat separately. And so that was called spin.
Okay.
But it turns out they were wrong.
Yeah.
The electron's not spinning as far as we know. We can actually calculate what the maximum magnetic moment and okay, we don't know the size of the electron, but we can definitely say it's smaller than this. And of course we know the charge of the electron. And so we can say if we had that charge, if it was all on that maximum possible radius that the electron could have in its spinning, it wouldn't come close to making a large enough magnetic moment. So it simply cannot be a result of the electron spinning. It has to be something else. So our understanding now is that electrons have a fundamental magnetic moment. Electrons are tiny little bar magnets. So it's an intrinsic property. And so when we talk about spin, it's a misnomer. We're not talking about anything spinning. We're not actually talking about a magnetic moment, and thus we're not actually talking about any momentum. But we talk about them still like we are. Oh, yeah, I did have something in here, but this is actually important here. This is what our wave function looks like. It's product of R times the spherical harmonics. And I did not write either R or the spherical harmonics because those are crazy, right? You have to take like the Rodriguez polynomial and the associated Rodriguez polynomial, or you have to take the Legendre polynomial. I have that backward to make those. So I didn't write those equations out. But that's our state that is going to give us the energy, the angular momentum squared, and the angular momentum in the z direction. And so I have here the operators and the eigenvalues. Here I put E sub n, and here I expanded it. Did we actually do the derivative of like the n equals 1 wave function to show that you get this for the energy? Okay, I'm not going to go back and do it now, but this here is exactly in agreement with what Bohr came up with. Now you guys know the Bohr model, right? I didn't even talk about the Bohr model. But the Bohr model, Niels Bohr proposed that, well, let me give you the 20-minute background on the atom. You had 20 minutes. Perfect. We'll use the rest of the class right on that. Okay, so it was thought from the time of like Democritus that if you take material and you cut it in half, you keep cutting it in half, eventually you're going to get down to a fundamental unit that was called the atom because it means indivisible. And then I believe it was J.J. Thomson found that there were electrons in matter. And so they said, okay, not quite so simple. You have like a positive slurry, and then you have little points of negative charge to the electrons. And that's what makes up matter. So that's called the plum pudding model. And so then you enter Ernest Rutherford, and he has Marsden do the experiment where he makes a foil of gold that's like 10 atoms thick, really thin foil, and shoots alpha particles that are helium nuclei, at it. And the expectation is if a helium nucleus hits an electron, it's kind of like a bowling ball hitting a gnat. I mean, it might make a measurable change, but it's going to be really small. And if it misses, well, then there's no change. And so when they did the measurements, they found that most of the particles did not slow down one bit. They just went through as if they touched nothing. But some of them bounced off at crazy angles, including ones bouncing straight back at them. And so, as I know you've heard me say, Ernest Rutherford, when he was hitting the circuit talking about his great discovery, he likened the surprise to if you hold up a piece of tissue paper and you fire a cannonball at it and it bounces off the tissue paper back in the cannon. You know, that's just not what they expected. And so he said that plum pudding model, that the positive slurry with the little electrons, can't be right. It's got to mostly be empty space because most alpha particles went through and just didn't hit anything. And it must have something that's a very massive region that it's bouncing off of, because, you know, this is more like I have a gnat hitting a bowling ball instead of a bowling ball hitting a net. You know, the bowling ball doesn't change much to the stationary bowling ball. The gnat hit helium nucleus bounces off. And in fact, he did a lot of careful work, and he could actually determine what the radius of the nucleus was. And so he said, we have a completely different model now. It's like with the solar system, planetary model, where you have a nucleus like the sun in the solar system, and then you have the electrons doing circular orbits around it like planets orbiting the sun. Which is odd because I'm pretty sure at that time they already knew the planets weren't doing circular orbits, but that was his model. Then Niels Bohr, Danish physicist, came over and worked with him. Came over and worked with Rutherford, and they realized right away that there were some significant problems. For starters, if you had electrons doing a circle around the nucleus, the electrons accelerate to do a circle. And electromagnetic theory says if I have a charged particle accelerating, it's going to give off radiation, which means it's giving off energy, so its energy is going to drop. And so the electrons should be slowing down and coming to the nucleus in less than a nanosecond. So the fact that we have atoms with electrons orbiting them means that there is a significant problem. Then there were some other problems. The planets can orbit any old distance they want from the sun, right? There's no, has to be here or here, but can't be anywhere in between. But looking at the emission spectrum or absorption spectrum from a gas, you see that there's only certain energy transitions that are available, which means there's only certain energy states in the atom. The atom has quantized energies. And so Niels Bohr proposed that you had a quantization. And what he actually proposed was that the angular momentum was quantized. He said the angular momentum is, so Niels Bohr said, I got to figure out where I put down my stylus. I believe he said L equals NH bar. And based on that, he got exactly this energy. And as you have to show in your homework, he got the same radius as we find for the most probable radius, or distance, I shouldn't say radius anymore, but distance of an electron from the nucleus in the ground state. Now these are ground state. The energy, matches. Everything matches except for one thing. The angular momentum no longer matches. The angular momentum is not dependent on the same quantum number as the energy. And it's not integer multiples of h bar. So his quantum condition turns out to be the part that was wrong, but he gets the right energy and he gets the right, most probable radius. But Bohr's model was quickly understood to also have its errors, because Bohr's model would predict that you should have similar brightnesses for different transitions, and some transitions that should occur don't occur. And so there were some problems with Bohr's model, and so that's where the quantum model then superseded Bohr's model. So we've been looking only at the quantum model, but it's good to have some of that background and to recognize that this here exactly agrees with the Bohr model. Now, of course, we're going to end up with that's not the energy, but that's when we get a little more sophisticated. Now we get to the spin. So I was only one slide off of my little soliloquy on spin. So here's a picture. What's wrong with this picture? There's only one problem with the picture. It's something I've talked about already. Yeah, the electrons aren't actually spinning. It was proposed that this is what was going on, that the electrons are behaving like bar magnets because they're spinning. And so you'll notice because the electrons have a negative charge, you have to do the reverse of what the right-hand rule, right? The right-hand rule would have said that it's going like this, your thumb points down, because it's negative charge, you reverse it, and it's pointing up. Right? So these pictures match classical theory. And I said the problem is we know they ain't right. But the electrons behave like little bar magnets. Now we talk about the electrons as particles with spin. And we've already looked at the quantum numbers. We had L. L had values that were 0, 1, 2, 3, 4, 5, right? And then we had M, which I now need to call M sub L, because it's the magnetic number associated with L, that went from minus L to plus L integers. Now with electrons, it turns out that the electrons have a magnetic moment that goes equally above and below 0, but doesn't hit 0. And so in this case, we still have a difference of 1 between the M sub S's, but it's going from minus 1/2 to plus 1/2. Now, there's something here that is completely glossed over. When I have an orbital that is in the L equals 2 state, that tells me that I can have M sub L's that go from 2, 1, 0, minus 1, minus 2. Here, if I have M sub S going from plus 1/2 to minus 1/2, that actually suggests another quantum number. The equivalent of L, if it's M sub S, what would the equivalent of L be? Just words, just letters. So we have L and M sub L, And then we have m sub s. What else should we have? Okay. I just want to make sure that we're thinking about the logic of this. We had L, which gave us m sub L. This told us the angular momentum, and this told us the angular momentum in the z direction, right? So now we have, shows the same color, m sub s that tells us the angular momentum in the z direction due to the spin. What other quantum number should we have? And we're going to have the same rules. So remember we had the eigenvalues for L. What was the eigenvalue for L? I'll go back 2 slides. Oh, 1 slide. What's the eigenvalue for L? H bar times what? That was Bohr's hypothesis that was wrong. Okay, so I didn't do it because it's more convoluted. It uses the raising lowering operators and that kind of stuff to get there. So it's kind of convoluted for how it's done. And I didn't want to spend the time. And so the eigenvalue for the L operator is what I have in the brown box. And so square root of L times L plus 1. So over here for the spin, the angular momentum for spin is equal to h bar square root of s times s plus 1. And likewise, I put it in L instead of an S. That's an L. And for the record, this is a Z. So those equations still work out the same. But going back to our rules, L, the maximum value for m sub L was L. The minimum value was minus m sub L. Or minus, set backward, or crossed up. The maximum value for m sub L was L. The minimum value for m sub L was minus L. What are the minimum and maximums for m sub s? Negative s to s, which means that s must have only one value. S is always equal to 1/2 for an electron. So when you hear people say electrons are a spin 1/2 particle, that's what they mean. S is 1/2. In your chemistry books, it probably says S instead of m sub s. Is that right? Oftentimes we'll use a capital S and a lowercase s instead of an S and an m sub s. And that makes life a little bit easier because you don't have subscripts. But, so we use L, M, S, and M, or S and capital S and lowercase s. Anyway, electrons always have a spin of 1/2, which means the total angular momentum of the electron is always h bar times the square root of 1/2 times 1/2 plus 1. Of course, 1/2 plus 1 is 3/2. 3/2 times 1/2 is 3/4. So it's always equal to h bar times the square root of 3/4, or over. That is the angular momentum of an electron. There's no other options. And now when I say that's the angular momentum, what do I really mean? It's derived from the magnetic moment. And then you have m sub s, is 1/2 or minus 1/2, which means that the angular momentum in the z direction is going to be either h bar over 2 or minus h bar over 2. So the electron is a two-state system. Now, something else to know here. Enrico Fermi and what is it? PAAM Dirac. They calculated something that we probably won't get to in this class. The statistics, the way things behave if they have a spin of 1/2. And if it has a spin of 3/2 or 5/2, anything that's an integer multiple of, or excuse me, not an integer multiple of, but that is half integers, is something that is described by this work of Fermi and Dirac. And so we call them fermions, and electrons are fermions. One of the outcomes of the work there for fermions is that you cannot have a wave function if you have two identical fermions in the same state. So if you have identical fermions, they can't be in the same state. What makes a fermion identical? All electrons are identical, right? But if I can say this electron belongs to this atom, and this electron belongs to this atom, now I have a way of differentiating them. And so there's no problem with, because when I was in high school and college, I had a problem getting this straight. There's no problem with this hydrogen atom having an electron in the n=1 state, and this one having an electron in n=1 state, because they're differentiable. You can tell one from the other. But I can't have a helium atom with two electrons both in the exact same state. What do you call that? Yeah, Pauli exclusion principle. The Pauli exclusion principle is a statement of this result of the Fermi-Dirac statistics. And so it applies to all fermions. Now we can also have particles that have spins that are integer multiples, that have spins of 0, 1, 2, 3. And if they have spins of 0, 1, 2, 3, what's the difference? Symmetric versus antisymmetric. And so Albert Einstein and Bose, his first name starts with S and it's long. They worked on the statistics. My understanding is Bose was the one who did pretty much all the work. But he passed to Einstein to say, what do you think? And so he and Einstein then collaborated, but it's basically Bose's work. And so we call particles with integer spins bosons. Particles with half integer spins, fermions. And bosons, there is no such thing as the Pauli exclusion principle. You can have a wave function if you have two bosons with exactly the same quantum numbers. And so that leads to some interesting things. Have you ever heard of a Bose-Einstein condensate? A Bose-Einstein condensate is what causes you to have things like superconductivity or superfluidity. And it's when you have all of your particles are bosons and in the ground state. So if they're all in the same energy state, that's where you get these cool things. That can only happen if you have boson particles, not with fermions. And so something like helium-4. Helium-4, if you add up the spins, protons are fermions that have half integer spin. Neutrons are fermions that have half integer spin. So if you take the nuclear spin, you're going to have 1/2 plus 1/2 plus 1/2 plus 1/2. Guess what? That gives you an integer. And so a helium nucleus, and also with 2 electrons, it still works out. But the helium is a boson. And so if you cool helium enough, you can have all of the helium atoms in the same state.
Wait, neutrons are also fermions?
Yes. Protons, neutrons, electrons are all fermions. That's easy to understand. But if you have superconductivity, this is electrons. Electrons are, as you know, fermions. You cannot have all the electrons go to the ground state. You have to have them build up, build up, build up, build up. And that's why we have things like the band structures if you have a crystal. Well, Cooper came up with a solution for that. He said that if you have 2 electrons, they can form kind of a bond between them. The bond is almost like a metallic bond where it's a matrix bond. It's not this electron's attracted to this electron. It's that the matrix, the rest of the material, holds them together. But then those two traveling together, what's the spin of two electrons combined? It's an integer, it's 1 or 0. And so the electrons, two electrons bound together in a Cooper pair forms a boson. And so if you have these Cooper pairs, you cool your metal down enough, the electrons can form these Cooper pairs, which are then bosons, and they can all collapse down to the lowest energy state if you get really cold, and then you have superconductivity.
Cool.
So this stuff we're learning here has a lot of implications, not just, well, it's the underlying, things for chemistry, but it has a lot of different aspects that, you would never have guessed. And look, in one quick minute, yeah.
You put S is equal to H bar over 2 or 3. Did you mean L?
Yes. Yes, I meant L.
Okay.
Okay, so this is our last line we'll look at. The real observable for the energy states of an electron in an atom, I say an electron in an atom, but what really has the energy? It's the nucleus and the electron. It's a combined thing. And if you have more than one electron, it's still a combined thing between everything. You can't say, oh, it's only the electron. It's an energy held between them. The only way we really have of probing those is by looking at things like the absorption or emission energies. And so, I talked about the quantized energies. When you look at the energies from hydrogen gas, you only have certain colors, and using the equation E equals HF as per Planck, then these are associated with specific energies. And so we can say is, okay, there is an energy gap equal to 1240 divided by 410 electron volts. Another energy gap equal to 1240 divided by 434, and so on. So we can get the sizes of the gaps. So we can directly measure the sizes of the gaps. Now, if we take the equation that we got for the hydrogen atom energies, we can plot what the energies are for n equals 1, n equals 2, n equals 3, and so on. And then we can calculate what the gaps should be. And so this is showing all of the gaps that end at n equals 1, all of the gaps that end at n equals 2, n equals 3, n equals 4. And those gaps, based on, the Bohr model and then the quantum model, match experimental observation to within a limit. And if we have time, I'm sure we're not going to get to perturbation theory. But with the advanced quantum model, they match pretty much exactly. And yeah, the way I've always run this class is if there's physics students, they have 4 units. And so they have one more lecture a week. If you have physics students, you guys just don't have class for the last quarter of the semester so that they can continue on. And that's what I have them do is eventually calculate the full energy spectrum using perturbation theory so that we can actually check it against reality. Okay, we're done for the day.